Historically speaking, this Physics Live started as a Physics Friday Live. Here's Baji. Hi, welcome. But then we cover physics on most days now, actually. So just for fun, we go live on most days and we cover physics topics on most days. So it's no longer just a Friday thing now, but here we are. Hello. Hi, God is the best. So is family. Hi, how are you? How are you doing? Hello, everybody. Welcome, welcome. Thank you for joining. Thank you for being here. Hi. Hi, Christopher. Hi, Christopher Sarantos. Hello. Thank you for joining. Hi, Lala. Lala says hi. Hello. Hi, Gabrielle. Hi. How are you doing? God is the best. So is family says hi. Hello. Hi, Preston. God is the best is saying OMG, I love your videos. Thank you so much. Thank you for watching. Thank you so much. Preston 2K28. Hi. Hi, how are you? Shadow, hi. Of course. No problem, says God. Thank you. Jesse Outdoors Adventure. Can you shout out my channel because I'm trying to spread Christianity and the outdoors to people? Oh, wow. I love the outdoors. Thank you for joining Jesse Outdoors Adventures. I love the outdoors, hiking and things like that. Thank you so much for subscribing. God is the best. Hi, Lily Hoke. Hello. Hi, Douglas. Hey, sweetheart. You like what you see. Hi, Scarlett. Hi, Preston. Why is my mom hiding the Tide Pods from me? Hi, Lala. Hi, everybody. Thank you so much for joining. Some of the messages are being held for review. I see. I'll have to tap on it to see that. Let me just share the live real quick. How is everybody doing? Hi, Lala. Hello again. Hi, Scarlett. I think I just, I think I saw, oh, wait. Sorry. Why is my mom hiding the Tide Pods? Says Preston, Squidward. I'm the real Squidward. Hi. Hi, Squid. I love you so much. Thank you, God. Hi, Antonio. Hi, Lily. Praises for us, for US. Shadow says good. Kev says pretty. Thank you. Love your videos. Thank you so much. God loves you. Thank you. Well, thank you so much. Really appreciate it. Thank you. I think I saw everybody. Kev King, Squidward, God is the best, so is family. Shadow, Lily, Antonio. Welcome. Welcome everybody. Preston, Lala, Scarlett, Douglas, Jesse Outdoors Adventures. Thank you so much. Okay. Pretty toes. Okay. Well, all right. So here we are. I shared the live, so hopefully people are seeing, getting the notification. And hi, Shadow. Thank you. I love the emojis, Shadow, the purple heart, as well as the moon. Love it. Join us and chat. I will say to my channel, God is the best, so is family. Shout out, please. I love you. Okay, thank you. Thank you, God is the best. Thank you, Shadow. Okay, so today, lately, I started to cover the topic of particle astrophysics on this channel. So this is a cats and books type of channel. We've covered a bunch of books on the channel, a bunch of topics. Hi, girly. Oh, hi. Black Queen says, hi, girly. Hello. Hi, Black Queen. How are you doing? Thank you for joining. Welcome in. Welcome, welcome. So we've been covering a bunch of different topics, especially from different books, but especially kind of focused on physics, astronomy, astrophysics, and cosmology on the channel. We've also covered some more light, casual topics like murder mysteries, actually, a while ago, I think the month of maybe August or September. But then pretty much we started to cover more and more science and physics topics because that's my background and people have seemed to enjoy it. So if you're interested, by the way, in finding these previous live streams, they're all under the live tab on my channel. Hi, Fuji. Fuji's calling to me. 1 second. Fuji Baba. Yes, Baba. Fuji wants to bring me his toy. Hi, Fuji. Where's my gift? Hi, Shadow. Hi, Shadow. Hi, God is the best. Fuji. Where is my toy? Sorry, I have to talk to him for a second. Otherwise, he'll feel like mommy doesn't give him enough attention. Babu? Fuji Baba. Did you bring me your gift? Okay, I think he's good now. So, Nicholas, hey. Is my hair pretty? Thank you. I didn't do anything. I washed it a few nights ago, but that's about it. Fuji Papa. Fuji. Bye, baby. As in, hi, baby. I don't want to say bye to you. You hang out with mama, okay? Where's Baji? Where is Suji? Oh, look at that. Suji's over there. Hi, Skylar. Skylar says background. Is that what that is, BG? So anyway, let me recap sort of what we've been talking about on the channel a lot. So we've talked a bunch about the physics, astronomy, astrophysics, cosmology type of topics. And in fact, if you're interested, especially in the month of November, we covered a lot of what we call modern physics topics, which are sort of the pre-World Wars type of physics, or sometimes I call it 20th century physics. It's mainly the early 1900s, including relativity, special relativity, general relativity, how those types of things progressed, as well as quantum mechanics, how those types of sciences and developments happened. Dog or cat? This one's a little kitty cat. Oh, there's my show that I was watching. Here is Baji. And here is Suji and Fuji. So all kitty cats here. Sorry for the crazy camera movements here. Okay. I'll try to keep the camera calm and just leave it alone while I'm speaking with you guys. So in the month of, oh, wow. Well, congratulations and thank you so much for adopting a kitty cat tomorrow. Adopting a pregnant cat tomorrow. Wow, that's awesome. Thank you so much for doing that. Yay, Skylar. So in the month of November, we covered a bunch of topics, especially in 20th century physics, relativity, quantum mechanics, those types of things. And then it all kind of precipitates into something like particle physics in the later part of the 20th century. So because of the big successes of quantum mechanics and its development in the 20th century, we have now what we call particle physics and a lot of development in particle physics. So we are able to talk about that now. I have a cat too. Oh, God. Oh, I was going to say that too. It's okay. Hi, Anahi. I have a dog and her name is Chanel. Oh, wow. That's awesome. Yeah, so keep your comments coming. If I don't read them right away, I will definitely read them. I usually read every comment. And I'm happy to see everybody's participation and engagement during this live chat. Um, I'm gonna keep talking about my topic here, but at the same time, I will be reading all of your conversations. And sometimes people even get into very lively chats with each other in the live stream sometimes. So I'll continue. Basically, in the 20th century, we made a lot of progress. Somebody in the live stream actually said yesterday that we especially saw a lot of theoretical physics type of progresses in the 20th century, especially like the entire field of quantum mechanics kind of saw leaps and bounds. And even though things were considered to be kind of bizarre by a lot of theoretical physicists at that time, things still succeeded because also those things were shown experimentally. So because of all the experimental successes, certain fields really saw a lot of progress. And I keep mentioning it, but it's really quantum mechanics is that field that saw a lot of progress and precipitated into something like what we have particle physics now. So particle physics, in a very quick summary, gives us the different families of particles or different families of fundamental particles. And there's pretty much three types of fundamental particles, and these are leptons, quarks, and bosons. So we've talked about this before. I'm just kind of recapping because we'll go into a little bit of a particle physicsy type of chat in just a second here. Hi Doro says, dang, no one is fighting yet. Yeah, I know, everybody is being so peaceful tonight. Hello from Belgium. Indeed, we're in Belgium. You're the best. Thank you, Anahi. J Station 2 says, what's up, chat? Bless up. Thank you. Anahi says, okay. Yes, there's usually a ton of fighting. So, well, not always. It really depends on the day or the night as far as these live chats go. So, pretty much, now that we have a more formal family of particles, so I mentioned leptons. So these are the type of fundamental particles that include, for example, the electron is an example for lepton. So is the neutrino, actually. So that's a lepton. Then we have quarks. These are also fundamental particles. In fact, some examples of quarks would be the ones that make up protons and neutrons, which are in the nucleus of course, atoms that you and I are made up of. And then lastly, we have the other fundamental particle, the third fundamental particle called bosons. These are, an example of a boson is, for example, light. Light has a particle nature called photon, or a quanta of light, and that photon is in fact an example of a boson. Now, I just gave you some examples of each family of particles. There are more such examples belonging to each family of particles. Next, I wanted to mention about particle astrophysics, which will be sort of the topic today. We will cover actually a chapter out of my own thesis in particle astrophysics. I called it Studies in Particle Astrophysics, my thesis, and I've been talking about sort of introducing particle astrophysics as well as introducing a specific source. Or a specific type of event, in fact, a transient event in particle astrophysics called gamma ray bursts. So we actually covered gamma ray bursts for around 4 hours, a couple of live chats ago. Oh, hi. Hi, Michael. Michael Fryer says, hi there, watching you from Australia. Ooh, awesome. Welcome to Australia. Anna, he says, you're welcome. Hi, Grimace. Hi, Birdie. Hi, Reese. Oh my gosh, Reese from Belgium is here as well. Amazing. Anna, he is here. God is the best. Sorry, I'm back. Physics, only physics I care about is the heating of grease at McDonald's. We need to make amazing food. Sorry, what I was gonna say. Forgot what I was gonna say. Okay, so basically... It's okay, guys. The banter is here. Oh, wait. I know that you are ending your things. I'm ending my things? I'm not. We're just getting started, actually. So, a couple nights ago, we talked about gamma ray bursts for approximately 4 hours. So, we will actually not talk about gamma ray bursts in a lot of detail tonight, but I wanted to mention that gamma ray bursts are an interesting source in particle astrophysics. Now, let me just give you a quick recap of what we've been talking about and what do I mean by particle astrophysics. So, now, generally speaking, astronomy and astrophysics historically have been done with something like visible light. This is the visible part of the spectrum of light, or what we can see with our naked eye if we look up at the sky. There are other parts of the spectrum of light, other wavelengths of light, such as gamma rays, X-rays, UV rays, that we can also utilize in order to study astrophysics and astronomy. And something like, for example, using gamma rays is actually part of particle astrophysics because gamma rays have very small wavelength. They are much more like the photon nature of light than, say, radio waves. So if you did astrophysics with gamma rays, that might fall under particle astrophysics. So pretty much particle astrophysics is basically doing astrophysics with particles other than traditional visible light. Now, this could be other wavelengths of light, or it could be completely different particles, such as neutrinos, a lepton that I mentioned a little while ago, as well as something like cosmic rays, which are charged particles that are hitting the Earth and can often have extragalactic sources. So, yes. So, what year is it? I think it's 2025, but but yeah, anyway. So basically, that's what particle astrophysics is. We will now cover a little bit more about particle astrophysics, but I wanted to give you a little bit of a recap of what you can expect and what we've been kind of covering and going into. So, oh wait, I know that you're ending what things? Hello, Doro. Hi, Doro. Hi, Doro and Reese. Please meet each other. I think you've met each other already, but here you go. She's adding the video. No, she isn't. She goes until like 2 a.m. Wow, 12 likes already. You're on fire. Thank you, Nicholas. Good evening to you and your too cool cat. Thank you. Hello, what year is it? What is meant by wavelength? So photons travel like an actual wave. So photons are photons are basically light particles. When light pretty much acts like a particle, we can call it photon. Photon has dual, or light has dual particle and wave nature. So if something has very, very small wavelength or a very, very high frequency, you can think of it as a particle. Pretty much it's almost like, if you have heard of Geiger counters, you can pretty much count however many times you're getting hit by a particle. And something like gamma rays would basically act, so basically gamma rays have very much high frequency, and that pretty much translates to a very small wavelength because the speed of light is a constant and the wavelength times the frequency gives you speed of light. So because speed of light is constant, if you have very big or high frequency, you will have very short wavelength. So at those very high frequencies or short wavelengths, such as with gamma rays, light acts much more like a particle. So we might as well count that as part of particle astrophysics. So that's what I was saying earlier, is that if you're looking at using light in the visible wavelength, then that might be more under the realm of traditional astronomy or astrophysics. But if you're looking at light in the realm of gamma rays, then it's kind of like doing particle astrophysics. Or you could just do particle astrophysics with a completely different particle, such as neutrinos, which is what I did my thesis in, and we'll read about that. And that's also particle astrophysics, as well as you could do particle astrophysics with something like cosmic rays, which are charged particles, could be just protons or even neutrons or some other type of atom. that's coming from extragalactic sources at high energies hitting the Earth. So I'm so stoned right now. I think I'm going to hit the waves, dude. Like, yeah. Yes, please enjoy our physics chat, Mad Hatter. I think this will be good. High energy. So since we're going to be talking about ultra high energy physics today, I think you're in the right place, Mad Hatter. So I started to talk about particle astrophysics earlier. I will give you a little bit of an introduction where I repeat what I kind of said earlier, and then we will go into the exact experiment. Is it possible to visibly see light traveling? Like with super slow motion cameras, is it too fast? So when we see something, that is the light that is being emitted or reflected back from that object. So perhaps I'm not following exactly what you mean, but yeah. I'm not sure. Let me talk about this introduction, and I'll keep thinking about your question. Yes. Okay. Perfect. So, exciting astrophysics. So I'm reading from my thesis now called Studies in Particle Astrophysics. Exciting astrophysics, according to me, happen far, far away. We live in a boring part of the universe. This allows life and the life sciences to thrive here. However, everything that is interesting in astrophysics takes place far, far away. For example, most gamma ray bursts take place about 1 gigaparsec away from us, which is over 3 billion light years away. So speaking of the speed of, or the question about light, it would take light 3 billion years to reach us from gamma ray bursts. Why are gamma ray bursts interesting? Well, in short, they are nature's most powerful accelerators, and they outshine an entire galaxy when they occur, with luminosity of around 10 to the 52 erg per second. It's a unit we use in astronomy. What is more, the physics behind these exotic events continue to remain mysterious for over 50 years. So we actually looked at the gamma ray burst chapter of my thesis recently. So you might have already caught that live already, but I'm just giving you a little bit of a recap. I'm not going to talk about this full chapter, so if you've heard it already, I'll keep it short. Traditional astrophysical messengers are not able to completely probe physics that take place at the farthest distances and at the highest energies. Since the beginning of astronomy, we have relied on optical light to study objects in the sky. In the last few decades, we have started utilizing light of other wavelengths, such as X-rays and gamma rays. However, light of energy 1 MeV and above can undergo pair production. It's a thing. Light of energy 13.6 EV gets absorbed by hydrogen atoms, the most abundant element in the universe. By the way, this is going to be a quiz question later on. I've asked this before, and I'm going to ask you again later tonight. What is the most abundant element of the universe? It's hydrogen, guys. Light is the astronomer's best friend, but there is an inevitable need for complementary messengers. So I'm like building up the case for other particles as messengers of astronomy. What? Fortunately, in the last century, we have opened up multiple new windows to peer into the universe. About 100 years ago, cosmic rays were discovered by Victor Hess in a balloon-based experiment. In the last several years, the IceCube Neutrino Observatory has discovered the first astrophysical neutrinos up to energies of a few PeV, which is 10 to the 15 eV. Moreover, gravitational waves were discovered by the LIGO collaboration in the last few years, confirming, for example, the association of short gamma ray bursts with neutron star mergers. So we talked about gamma ray bursts recently from that gamma ray burst chapter. When LIGO measured gravitational waves for the first time several years ago, so within the last decade, so this is very recent stuff, guys, that was the first confirmation that short gamma ray bursts are associated with neutron star mergers. Before that, that was just a theory. So this was very exciting and gave us an example of multi-messenger astronomy, where we use basically light, gravitational waves, other things, all of that to do a multi-messenger type of astronomy. So that's what we call oh, the delay from the torch being turned on and the surface it faces lighting up. Yeah, I don't see why not. I don't know of any such, I mean, it really depends on how far away the source is. We basically make measurements like that in astronomy. If you know, if the torch is like a source of interest in astronomy, the speed of light is needed to make all the delicious food. That's an unfathomable distance. Where am I, dude? I'm like in the 12th dimension. How did I get here? YouTube really has to fix this. This channel is peak YouTube. Oh, thank you. Cutting her friends off psychically? The most common way to get a gamma ray is through the process of radioactive decay from unstable atomic nuclei. That's why SETI search for signals in the hydrogen radio band. What's a neutron star? So neutron star is a stellar remnant. So a while ago, we talked about how stars die. And depending on the mass of the star initially, the star's death will result in one of three end states, or stellar remnant, as we like to call it. This is white dwarf, neutron star, or a black hole. So if the star is pretty low mass, it'll become a white dwarf. If it's more massive, it will become a neutron star. And if it's even more massive, then it'll become a black hole. If you want more specifics, I can go grab my astronomy book and go over it again. But we did kind of cover that already. You know what? I'm in the mood though, so we will do this. Thankfully, my astronomy book is right here. Yay! I love astronomy! I was a closet astronomer in my first year of grad school. So they go big before they collapse, is that right? They supernova. Or wait, what did you just ask? So basically, depending on the star's mass, okay? So like, for example, our sun is a pretty small star, and it's also a very young star. So a star's life cycle, it goes through different stages. So first of all, it goes through different stages, okay? Now, depending on the stage it's in, the life cycle it's in, it might be getting close to dying. So broadly speaking, a star, obviously, there's two main things going on. There's gravitation. A star is a lot of mass, so so it can collapse on itself because of its gravitation. But generally, what keeps a star powered and going and not dying, for example, our sun is not dying. That's how we are here. We get energy from the sun because the sun is converting hydrogen into helium. So this nuclear power is what keeps the sun alive and going, and what gives us energy and what keeps us going. So if the sun were to be completely out of nuclear power, then it too would collapse and supernova and die. That's where elements are created. Yes. When the universe first formed, the only elements that we had were hydrogen and small amounts of helium and trace amounts of lithium. Every other higher, heavier element are all made in stars. Yes, you need stars to make the elements. Exactly. You got it! So our sun primarily makes helium from hydrogen by doing nuclear physics. Xenon, girl of the 21st century. I didn't see it either. So because thanks to the process in the sun, our sun, making helium from hydrogen, that's the nuclear power process going on in the sun, which keeps it going, gives it fuel. Because if it didn't have that fuel, it would actually collapse on itself under its own gravity, and it wouldn't keep on being alive. And pretty much when a star does run out of nuclear power, it will end up sort of collapsing on itself, causing a big explosion, and that is generally called a supernova. And after that supernova, after all that big explosion and things kind of happen, you end up with stellar remnants, which is basically a dead star. Okay, so like sort of not really a star. Hi, Sachi. Not really like a regular star, but more like a remnant, a stellar remnant. So now we can talk about the different stellar remnants since you asked, real quick. We know already that what they are. These are white dwarfs, neutron stars, and black holes, depending on the mass. So if you have you know what? I'm just trying to... Hi, baby. This part talks... Oh, let me read this part. This will be helpful. The life history of a star is determined primarily by its mass. If you know a star's initial mass, you know, at least in broad outline, how it will evolve. Other factors like the star's initial chemical composition and initial angular momentum have a smaller effect. For instance, the fusion history of a star depends on its initial mass. So pretty much if a star is below 0.08 solar masses, then it will have no fusion. The center of a low mass ball of gas never becomes hot enough for hydrogen fusion. This mass range represents not stars, but brown dwarfs of spectral type L and T. We can worry about that later. If you have a star or an object of mass between 0.08 solar masses and 0.5 solar masses, then this type of thing will do fusion of hydrogen to helium. The center of the star never becomes hot enough to fuse four helium to carbon and oxygen, because more heliums can make carbon and oxygen, but it doesn't get hot enough for that, for this type of mass. Stars in this mass range are M stars on the main sequence and will eventually end up as white dwarfs made of helium. So this is the star of mass between 0.08 and 0.5 solar masses. The cats want to play. She wants attention, yeah. Then if you have a star between 0.5 solar mass and 5 solar masses, then it will do fusion of hydrogen to helium-4 and helium-4 to carbon and oxygen. The center of the star never becomes hot enough to fuse carbon and oxygen to heavier elements. Stars in this mass range are A, F, G, and K stars on the main sequence and end up as, again, white dwarfs made of carbon and oxygen. So this is kind of giving you an idea. These lower mass stars will become white dwarfs when they die. Stars between 5 solar masses and 7 solar masses will do fusion of hydrogen to helium-4, helium-4 to carbon-12, and oxygen-16, and carbon-12, and oxygen-16 to Neon 20 and magnesium 24. The numbers I'm saying with the 20 and the 24 are the atomic the mass number, like the number of particles in the nucleus of that particular thing. So it's a nuclear physics type of way of saying things, not the chemistry way. Stars in this mass range are B stars on the main sequence, so this is between 5 and 7 solar masses. And then stars of mass greater than 7 solar masses will fusion hydrogen to helium-4 to carbon-12 and oxygen-16, carbon-12 and oxygen-16 to neon and magnesium to silicon, and silicon to iron and nickel. Stars in this mass range are O stars on the main sequence. Sorry. So the initial mass of a star also determines what its corpse or stellar remnant will be. The lowest mass stars become dense white dwarfs supported by electron degeneracy pressure. Higher mass stars leave behind even denser neutron stars, and the most massive stars of all end up as black holes, representing the ultimate in density. We will examine in turn the evolutionary roads that lead to white dwarfs, neutron stars, and black holes. We don't have to today, but that's what a neutron star is. That was my answer to Reese's question about what a neutron star was. It's one way to die for a star. There are 3 ways in which a star can die or become a dead star, depending on its mass. Neutron star is one type of stellar remnant. Okay. I used to watch Oh, it's not good, that movie. I used to watch Brian Cox documentaries when I was little. Everything I learned about space is literally from those. Is the sun going to explode? Eventually. Not right now. You don't have to worry about it right now. It's a very young star. Doro Madness, those ruled. Fun fact, 1.3 million Earths will fit into our sun. Is there a limit to how big a star can be? I don't think I can keep up with the physics tonight. I think it's time for me to hit the hay. Good night. So what is a pulsar? Yes. Yes. Well, hello there. Oh, hi. Hi, Crazy Sick Wine. I'm an ageless beauty. Okay. Yes, indeed, Reese. Reese, you better stay because of your questions. I'm losing everybody else in the chat. That's okay, which is completely fine. Completely fine. So, why does it start spinning? So, it's not that it starts spinning, it's how it was made. If it had angular momentum when it was formed, it will continue to conserve angular momentum. So basically, it's not about starting to spin. It was, let's just say, the way it was made, it inherited angular momentum. Okay, so because of conservation of angular momentum, it will, let's just say, continue to spin or spin faster because its geometry has changed. Because angular momentum, remember, has to do with sort of a distribution of mass, not just the mass of something. So, so yeah, it It spins because it's conserving angular momentum. I'm always mesmerized by your brilliance. Oh, thank you. Thank you so much. You guys better stay, man. Look at this chat. Everybody disappeared as soon as I brought out this book. I'm going to tell these authors on Facebook that everybody left the chat except for you 5 brilliant, amazing friends of mine. So anyway, next. No, I'm actually in the mood today. You know what? You know what? I'm coming out of the closet. I like astronomy. I do. And nobody can stop me. Ooh, so you were asking if there is a limit to how big or how massive a star can be. So pretty much, think of it this way. If a star is doing things nuclear-like, then it should be fine. If it gets too big, well, not really. If it basically starts to make very stable nuclei that don't want to further merge and make even more heavier nuclei, that's sort of when it's in trouble. Pretty much, if it stops doing nuclear physics, then a star's death is imminent. Because either way, it's a lot of mass for gravitation to not do its thing, right? So gravitation will make a star collapse on itself. And the mass ranges can be any of the ones that we just talked about. Pretty much, let me double check. I don't think I know of like an upper limit to how massive a star can be, to be honest. But I will think about this question more and think about if there is such a limit. Good question. So a star's lifespan is proportional to how massive it is. It's the way a star evolves. Yes, pretty much anything with a star, the life history of a star, and all the details basically of its life cycle is dependent on its mass. The mass is the most important thing, it turns out. So actually, we can now talk about something else. Because you're asking about the mass, there is an important thing we can discuss at this time. So, let me mention it in a way that is here. This is what we'll do. Now, I will say, that it depends on its compactness as well. Because if a very massive star, so remember, if it's a very massive star that's too compact, then it will become a black hole, right? So in that sense, if it's a very massive star and it runs out of nuclear power, when it collapses, because it gets so compact, and because, if it becomes compact enough where it meets the requirements to become a black hole, which is given by the Schwarzschild radius, something else we talked about earlier, then it'll just become a black hole. So at that point, it's a black hole, not a star. But a black hole is a stellar remnant. So it's related. Okay, so let me see if we can talk about the Chandrasekhar limit. Let me see that. I know it's part of this chapter, but I just want to introduce it. So give me 1 second. 416. So very important person in astronomy is Chandrasekhar. So, so, hi Tim. It has been a long time. So, there is a maximum possible mass for a white dwarf. So, let's talk about that. So, pretty much for stars, how are you doing, friend? Sorry it has been so long. I've been working my ass off. Love to see the channel still doing well. Thank you. I watch Anton for a lot of similar things. Oh, I don't know who Anton is, but thank you so much. Fellow Bostonian. Oh, hi. Hello. Welcome to Tim and welcome to Boston. Yay. So, you were asking about the mass limit for a star. So it's not quite a star because it's really a stellar remnant, but let's look at this part about a white dwarf. So, the maximum possible mass for a white dwarf, which is a type of stellar remnant, remember, when lower mass stars die, they become white dwarfs. Pretty much our sun will become a white dwarf when it dies. The maximum possible mass for a white dwarf is MCH, or M Chandrasekhar, which is around 2 solar masses. It's called the Chandrasekhar mass after the astrophysicist Subramanian Chandrasekhar, who was the first to calculate it. A more careful calculation of the Chandrasekhar mass for a carbon-oxygen white dwarf yields around 1.4 solar masses. So M Chandrasekhar is around 1.4 solar masses, but pretty much we say that the maximum possible mass for a white dwarf is 2 solar masses. Any star that can reduce its mass below the Chandrasekhar mass, generally by strong stellar winds during a giant phase. So basically, sometimes a star will lose mass because there are winds and it kind of like some of its mass is like blown away, pretty much. So that's what they're saying. Strong stellar winds during a giant phase will end as a white dwarf. So the star might have had more mass, but say in a giant phase, like sometimes a star may have a phase called a red giant or something like that. In a giant phase, it kind of just becomes more like fluffy, and some of its mass could get basically literally like blown away into space by stellar winds. And by the way, that's how we're here, because stars make elements and the mass, the materials within the stars get blown off into space. We are able to be made from those materials, reaching, for example, where we are. Hi, Suji Mama. Is everything okay? Okay, so it is estimated that stars with mass of less than 7 solar masses will be able to slim themselves down below the Chandrasekhar mass. This calculation is uncertain, though, since mass loss during the giant phase is irregular by nature and difficult to model. Stars with initial masses less than 0.5 solar masses will eventually become helium white dwarfs. Stars with masses between 0.5 and 5 solar masses initially will leave behind carbon-oxygen white dwarfs. Stars with mass between 5 and 7 solar masses will leave behind neon magnesium white dwarfs. So the white dwarfs, like richness of element, like whether it's made of helium mainly or carbon-oxygen or neon magnesium, it depends on this. Again, it depends on the star mass. It's kind of crazy how much things depend on the initial star mass. It will, that will affect the death of the star, how it dies, how fast, how soon it dies, the life cycle of it, as well as the richness of the element, or what basically makes up the white dwarf or the stellar remnant that is left behind when the star is dead. Solar mass is our sun. Yes. What is a solar mass with regards to size, the size of our sun? Yes, pretty much in astronomy, oftentimes, masses and things and distances are given in terms of our sun, because we have a sun. We just have the one sun, so it's rather special to us. And so oftentimes other masses are reported in terms of our sun's mass, even though our sun is really special, especially because we just have the one. But yeah, it's not that interesting of a star, which is good. That's why we're here. Because if it was sort of a giant or something like that, then that would be very inhospitable indeed to be near it. So yeah. So hopefully that kind of helps with the mass type of questions. White dwarfs, as a stellar remnant, pretty much what kind of initial mass will make what kind of white dwarf. Like even within white dwarf, you will have a variety of white dwarfs. So and with a variety of different elemental richness. And so hopefully that kind of helps. And Chandrasekhar, Subramanian Chandrasekhar gave us the math for that. I find novas and neutron stars fascinating. Oh God, that's what we're talking about. Yay. Novas and neutron stars. Yes, that's exactly what we're talking about. In fact, Reese asked about neutron stars, so I think we'll cover that too. Thank you, Nicholas. According to current estimates, our galaxy, the Milky Way, contains between 100 and 400 billion stars. Also that a killer nova is less bright than a supernova. Oh, well, you mentioned the big stars become black holes when they die. I wondered if there's something denser than black holes that come from even bigger stars. No. So pretty much black holes have a variety. So like a black hole can be, black holes have, they have their own sort of classes, basically, It could be a smaller mass, less massive black hole, a larger black hole, etc., etc. So pretty much what we know is that if it's a very massive star, the limit was, where was it? Stars with initial mass of more than around 18 solar masses or so will leave behind remnants with mass equal to mass max, which is around 3 solar masses for the neutron stars, I believe. So these ultramassive, ultraluminous, short-lived stars will leave behind black holes as their remnants. So pretty much you would make a black hole, and that black hole could have a variety of different masses. And remember that to be a black hole, you basically have to have a certain Schwarzschild radius. So there is a different math for that. We actually covered this a little bit when we talked about general relativity. Remember how Schwarzschild actually solved Einstein's equations exactly for a black hole, what they called a point star. Remember when we talked about Einstein's cosmos from that book we were referencing? And so really it depends on, basically if you have a very supermassive type of star, when that thing collapses, its collapse is a more extreme type of collapse than a more medium-sized star. So when it collapses, it's like, some shit's going down. And it becomes like, it has the tendency, it could become really compact, basically. All of that gravitation is now winning. over nuclear power. And so if it goes below the Schwarzschild radius, then it's going to become a black hole. And after that, the black hole can continue to eat more things and become more and more massive. So we can talk about that real quick as well. So the critical radius at which a mass m has an escape speed equal to the speed of light is called the Schwarzschild radius, or Schwarzschild, after the physicist Karl Schwarzschild, who first calculated it in a relativistically correct manner using Einstein's equations. We talked about that a while ago. Any object will become a black hole if you squeeze it until it is smaller than its Schwarzschild radius. So even you could become a black hole. Yes, but it is only theoretical right now. Black holes are dense, but there is a theory about a dark matter star. However, our knowledge of what dark matter is. So black holes are not theoretical. Black holes are experimentally proven. As far as dark matter, yes, we do not know what dark matter is, and we have definitely covered dark matter as well as dark matter candidates in other live streams. So if you're interested in dark matter and dark energy, we covered that a lot as far as, you know, what kind of research is being done, or what do we know, / what have we kind of talked about, thought about, calculated, etc., in some other live streams in the months of November and December. Who sings the song Champagne Supernova in the Sky? I don't know. Oasis. The song We're All Made of Stars comes to mind. Moby. I want to do a chicken nugget. Okay. Yeah, black holes are. I was strictly talking about dark matter being theory. Yes, correct. Yes, thank you. So basically right now, so since Tim has brought this up, basically right now in astrophysics cosmology, both topics, I would say, basically astrophysics has a different approach to, say, the topic of dark matter than would cosmology, because cosmology is the study of the universe at a much larger scale, including the sort of beginning of the universe, early universe, its evolution, large scale structure, etc., etc. So the topic of dark matter is interesting because it can be approached sort of in an astrophysics, astronomy, or cosmology manner. But we have seen and talked about it from these different approaches, and we found that so far we don't really know what it is, but there are certain models and calculations that were done, and we were able to see that in cosmological models, it turns out that dark matter is a dominant part of the universe, much more than ordinary matter. So there is these different evidences and different math and models that we have. But for sure, the open questions that are currently the biggest open questions, I would say, in this topic of either cosmology, astrophysics, or even physics, or just in the universe, are what is dark energy and what is dark matter. So those two questions are definitely open at this time. We don't know what dark energy exactly is. We know its effect. We know that it makes the universe expand, but we don't know exactly what it is physically. And then we also don't know what dark matter is. What is the sort of physical meaning or nature of dark matter? We don't really know what it is. We have certain evidences that point to the existence of some invisible some invisible matter, but we call it dark matter, and we don't know what it really is. Deduced its existence through calculation of its effects on other stuff. Yes, so I talked about that orbital speed curve in the past, which is one of the evidences of dark matter. We also looked at how dark matter is something that we would need from a cosmology point of view as well. So it's not just an astronomy thing, it's also a cosmology thing. Maybe the universe is inside a huge black hole. That could be, that very well could be, but we would still want to know what this universe is kind of doing, even if it's inside a black hole. Deduced its existence through calculation of its effect on other stuff. Maybe the universe is inside a black hole. Peter, hi. How is everyone doing? I'm doing great. Yes, hello. How are you? So yeah, these are very interesting points that you guys are bringing up, and I'm glad you are, because yeah, for sure. So we will revisit the topics of dark matter and dark energy again, for sure, in these lives. I mean, those are such interesting topics. But as you said, completely valid. Someone brought it up, Tim, here, which is that we don't know what dark matter is. Dark matter is a theory in that sense that we don't know what it is. There is experimental evidence, or observational evidence of the fact that there is missing matter or invisible matter even within our galaxy. So we talked about it. I'll just recap. We basically found that there is evidence of invisible matter even within our galaxy. And then from a cosmology point of view, we saw from different calculations that you actually have this other type of matter, which is the more dominant matter, which fits our cosmological models, which explain our current state or the evolution of the universe. And then there is even evidence that dark matter might play a role in large scale structure formation, and also the formation of various types of galaxies, which is where it becomes really interesting. So understanding, so if you're researching dark matter, this is amazing. And honestly, if you're researching either dark energy or dark matter, I mean, those are the biggest open questions of our current world, of our current universe. Every time you say cosmology, I think of my other field, which I work, which is cosmetology, and I have to catch myself. Oh my gosh. So when I when I was studying cosmology in grad school, I would Google things, and more often than not, cosmetology would come up. So yeah, the cosmology we talk about here has nothing to do with makeup or Garnier, Nutrifess or whatever. It's cosmology, the universe. But no, that's a great point. I'm glad you're validating my own experience, which is that more often than not, people think about cosmetology or cosmetics. Yeah, not the study of hair, lol. Yeah, no, seriously. Hi, Peter. What an unbelievable wife. Oh, gosh. You would make, I'm simply in a trance. Okay. Thank you. Good to be here. Thank you. I wish this live was around when I went to school. Yes. Well, evidence says that I would not be a very good wife, actually. Or, well, I don't know. I don't know what I'm saying now. Words are coming out that are not very well construed. Every time you say cosmology, it's definitely the late crowd. Yes. Yeah. So basically, loving all the gooning. What? What is that? What is that? So it is actually a favorite topic of mine to look at dark matter from various approaches. And if you look at it from an astrophysics point of view, so this is one way of explaining it. Basically, if somebody were to research dark matter within, say, our own galaxy or in our nearby galaxies, then that's sort of an astrophysics or astronomy approach. But if you were to think about dark matter as it affects how our universe has evolved, how it affects large scale structure, because we also looked at how the distribution, so get this, the distribution of galaxies in our universe is not random. The universe not only evolved from a baby universe to the way it is now, it has gone through evolutions, it has gone through stages. It used to be radiation dominated, then it became matter dominated, now it's like dark energy dominated. But also the distribution of galaxies, which is something we can like measure in the universe, is not random. There is a meaning to this madness. And so I feel that some people probably study dark matter just in the context of how it affects large scale structure. And that is a cosmology approach to dark matter. So if you're doing that, then congrats. I think that's really cool, and continue on. And yeah, this type of live stream is hopefully helpful for things like that. The universe is nothing but random. You are nothing but random. Don't you dare. Don't you dare. We're having a serious conversation. Don't interrupt with your whatever it is. The distribution of the universe's mass is maybe the key to figuring out. So that's what I'm saying. There are multi-pronged approaches to figuring out what dark matter is. It's a multi-pronged approach, right? You can look at it in terms of effects on our own galaxy. You can look at it in terms of effects on our neighboring galaxies. Or you could literally try to figure out why our universe's distribution is the way it is in terms of the galaxies. And of course, all the galaxies, all of us, we are all made of ordinary matter. The stuff that gives luminosities for us to pick up on, the stuff that interacts with light, so we can measure it with light. And then there's, of course, other ways of measuring things too, like, for example, with gravitation. And we did that. And that's how we know that there is dark matter. Exactly. So because we want to know how the universe works. Exactly. So I've never understood the practicality. Well, astrophysics is not practical. Generally speaking, astrophysics, cosmology, astronomy, we don't have the burden of being practical. We have a privilege, which is that we can think and do cool things without being useful to anybody. Now we will talk about neutron stars, another useless thing, but lovely thing, just amazing thing. What happens to stars whose initial mass is greater than 7 solar masses? Amazing. There aren't many stars that massive. Well, keep the live chat engaged. Thank you so much. What happens to stars whose initial mass is greater than 7 solar masses? That's 7 suns, guys. Our sun, 7 of them. There aren't many stars that massive, but they do exist. I have no idea. I have thoughts about dark matter, but I do not know what is gooning. Okay. You asked about neutron stars, Reese, my boy from Belgium, so we will talk about it. This is going to be a weird connection, but it is a fun fact. With the study of dark matter and this idea of wormhole travel and every theory of our universe versus the potential of neighboring ones was the entire basis behind the writing of Transformers, Cyberton, was the entire basis behind the writing of Transform. I don't know. Is that like science fiction? I don't really read much science fiction. I keep my entertainment life and my professional life strictly separate. The wormhole thing comes from string theory. Yes, you've been listening. Wormhole is an Einstein-Rosen bridge. It's not real. Yeah, sort of. String theory is a little bit more modern, but yes, a wormhole, if I remember correctly, a wormhole is an Einstein-Rosen bridge. So Einstein and Rosen, his student, came up with that. Alice in Wonderland has a wormhole, if I'm remembering any of it correctly. String theory, so when Einstein was around, unfortunately, string theory didn't really take off. So when Einstein was doing all that stuff and trying to come up with the grand unified theory, which he did not really finish, and he was working with his students, and then later on, those people kind of dabbled in higher dimensions, and so there was a baby string theory around, but there wasn't really the full-on string theory around when Einstein was around. So it wasn't until after he died, decades, sort of like 30, 40, 50 years later, is when superstring theory became a thing. So wormholes are older than that. So yeah, I'm answering the question about the wormhole thing, but I don't know. Transformers is a way of life. I don't really know. Hi, Disco David. Hi, Reese. I don't really know what the transformer thing is. You realize the chat is Googling everything. They simply know nothing of physics. Oh. But anyway, we talked about wormholes as well. Who do you think would win in a match? Oh, thank you. Yes, Reese. Okay, we will go back to our discussion now, my boy, which is neutron stars. What happens to stars whose initial mass is greater than 7 solar masses? There aren't many stars that massive, but they do exist. Very massive stars have short lives. So you were asking about the lifespan of stars. So yeah. Very massive stars have short lives and die spectacularly, leaving behind a badly crushed corpse. The main sequence lifetime of a massive star is short. There is an equation for it. It's like 30 mega years times m over 7 solar masses, all to the -3. Life after the main sequence, when the star... So main sequence is a part of the life cycle of a star. After this main sequence, the star becomes a supergiant. So pretty much its life cycle after becoming a supergiant will be very short. It doesn't stay as a giant for very long. Duraduro was feeling sick. Stay with us. Listen to this live as like a meditative background. I will make my voice calmer too, and whatnot. Life after the main sequence, when the star becomes a supergiant, is even shorter. The ultra-luminous supergiant is relying on less efficient energy sources. Fusing hydrogen to helium releases about 6.4 times 10 to the 14 joules per kilogram. Thereafter, fusing helium all the way to iron releases only 24% as much energy per kilogram. So that's the thing. It's almost like these stars that made the heavier elements that then made us sacrifice themselves, because when you make those heavier and heavier elements, you're actually becoming less and less efficient in powering yourself. And ultimately, you will collapse upon yourself as the star. So in its last moments as a star, a massive supergiant has many concentric fusion layers over an iron core. That's right. There's an iron core has a heart of iron. A schematic diagram of such a star is shown over here. Basically, this is showing that there is an iron core, then there's a silicon fusing shell, then there's an oxygen fusing shell, neon, can I say that? Neon fusing shell, carbon fusing shell, helium fusing shell, and of course hydrogen fusing shell, central fusion region. A supergiant star such as Betelgeuse, which is spelled as Betelgeuse, so like Betelgeuse. Somebody mentioned Betelgeuse. Here it is. When will Betelgeuse die? I hope it stays alive. It's probably already dead. Just the light from its supernova might not have reached us yet. FYI. As we saw, a supergiant star such as a Betelgeuse, can have a radius of over 1,000 solar radii. So you know how big the sun is? Imagine like 1,000 times bigger than that. That's basically in the realms of being a giant. Stars that are on the main sequence are much more like, normal size. Once it becomes a giant, it's really gotten super fluffy, and it might have a radius that's like 1,000 times bigger. Ian, hi. Hi, Ian. Hi, Duro. Hi, Reese. So, models of stellar evolution indicate that the dense central fusion region of the supergiant has a radius of less than 1 solar radius. That's the central fusion region, okay? The central iron core is very dense. What? The central iron core is very dense, thousands of tons per cubic centimeter, and is supported by degenerate electron pressure. So we can talk about what degenerate electron pressure is, but basically things are very compact in that core. The iron core continues to grow in size as the silicon fusing shell eats its way outward in the supergiant. When the iron core reaches the Chandrasekhar mass, quiz question, what is the Chandrasekhar mass? It's around 1.4 solar masses. It is no longer, when the iron core of such a supergiant type of star is itself reaching the Chandrasekhar mass limit, it is no longer adequately supported by the relativistic degenerate electrons, and it starts to collapse very rapidly. The collapse time at the high density of a degenerate core is less than 1/10 of a second. Look at that. Are you ready for a collapse? As the density of the collapsing iron core rises, protons and free electrons start to combine to form neutrons. One side effect of the collapse is thus a huge burst of electron neutrinos. Yay! A Chandrasekhar mass of iron contains around 10 to the 57 protons. So 10 to the 57 neutrinos are created during the collapse of the iron core, because basically this proton plus electron making a neutron plus a neutrino will be happening. This burst of neutrinos escapes from the star because neutrinos have a very weak interaction. They don't interact much. They can just go through the star. They can leave the star. This burst of neutrinos escapes from the star, carrying away a large amount of energy, about 10 to the 46 joules. Guess what? That's not good, because that's more energy just leaving. For comparison, the sun will radiate around 10 to the 44 joules of energy during its main sequence lifetime. So just the neutrinos from a star like this can carry away 10 to the 46 joules, which is more than what the sun will radiate total during its main sequence lifetime. Yay! The core is now a sphere of around 2 times 10 to the 57 neutrons that are essentially in free fall. Can anything stop the headlong collapse of the neutrons? Yes. Core collapse can be stopped by neutron Degeneracy pressure. Degenerate non-relativistic electrons have a pressure. This is because electrons are fermions. The Fermi exclusion principle applies to neutrons as well as to electrons. Degenerate non-relativistic neutrons also have a pressure. There are some equations for that. A sphere of neutrons supported by degenerate neutron pressure is called a neutron star. So this is another way of answering your question. What is a neutron star? It doesn't satisfy our strict definition of a star because a neutron star isn't gaseous and isn't powered by fusion, but the name has stuck. So we call it neutron star. It's not actually a star. It's a stellar remnant. It's a dead star, okay? A white dwarf, a sphere supported by electron degeneracy pressure, has a radius given by an equation here, 1:35 in the morning. By an analogy, a neutron star, a sphere supported by neutron degeneracy pressure, should have a radius. So there are some equations now. In truth, after some equations, things are a little bit more complicated than we've been letting on. The density within a neutron star is comparable to the density within an atomic nucleus. Thus, the strong nuclear force between neutrons must be taken into account. So, electron degeneracy pressure and neutron degeneracy pressure is not the same exact thing because there is a strong nuclear force. There's a strong force between neutrons. Although the strong nuclear force is attractive at distances d of more than 5 times 10 to the minus 16 meters, this attraction is what keeps nuclei from flying apart. So strong force. It is repulsive at shorter distances. So the neutron degeneracy pressure is more complicated. It's not just like the electron degeneracy pressure. Thus, the short-range repulsion between neutrons stiffens the neutron star. It makes it and keeps the neutrons from being shoved arbitrarily close together. So neutrons cannot be shoved any more closer together because of the strong force, which is repulsive after a certain point. For one plausible model of neutron star interiors, which takes the strong nuclear force into account, the mass radius relation is given here. White dwarfs contains the mass of a star squashed into the volume of the Earth. Neutron stars contain the mass of a star squashed into the volume of a small asteroid. It is a cliche for an astronomy text to show a neutron star juxtaposed into a city. Nevertheless, there's a reason why so many books include such a figure. It's an effective way of showing how tiny neutron stars are for their mass. Yeah. Understanding the structure of neutron stars is difficult for two reasons. So basically, this is Manhattan compared to a neutron star because the neutron star's radius is around 10 kilometers. Oh my gosh, that's nothing. A neutron star, what a bunch of misfits we are. A neutron star's radius is around 10 kilometers. Dude, that is so small. That is so small. Reese, are you paying attention? So the small that we're talking about now is the radius. Not the mass, not the mass. Understanding the structure of neutron stars is difficult for two reasons. Not only must the strong nuclear force be taken into account, but also gravity must be treated using general relativity rather than Newtonian gravity. The escape speed from a neutron star using the Newtonian formula is different, blah, blah, blah. Basically, neutron stars are relativistic. That's cool. Now we'll talk about your pulsar. Because the magnetic flux threading through the core is also conserved during collapse. So this is what I was saying. It's not that it starts spinning, it's because it conserves the angular momentum. So The magnetic flux threading through the core is also conserved during collapse. Neutron stars have strong magnetic fields. Compared to the magnetic field strength of around 10 to the minus 4 Tesla at the sun's surface, a neutron star can have a magnetic field of around 10 to the 6 Tesla. This is Nikola Tesla, guys, not the car. Rapidly rotating, highly magnetized neutron stars are pulsars. The name pulsar was given not because they pulsate in and out like Cepheids, they don't, but because they produce pulses of electromagnetic radiation as seen from Earth. Pulsars were first detected in 1967 during a radio survey of the sky. No one knew what they were at first. It was soon realized, however, that they must be neutron stars. Some pulsars have periods as short as a millisecond. Wow. But others have gradually spun down to periods of more than a second. The rotating magnetic field of the neutron star creates a strong electric field. This field is capable of ripping electrons and ions out of the neutron star's atmosphere and accelerating them along magnetic field lines. How interesting. Where they produce copious synchrotron radiation. Remember synchrotron? The synchrotron emission tends to be beamed along the two magnetic axes of the neutron star. Since the magnetic axis isn't aligned perfectly with the rotation axis, the beams of synchrotron emission sweep around and around as the neutron star rotates. Neutron stars whose beams of synchrotron emission happen to sweep across the Earth's location are labeled pulsars by Earthlings, us, since we detect periodic pulses of synchrotron radiation from them. So we're just detecting them as periodic. Hi, Reese. Hi, everybody. We've got people hitting on the girl and blatant racism. This is what I miss when I just listen. Do they get brighter? How do we even see these things? So that's what I've been talking about now. The pulsar thing. That's how we discovered them. Can I mod in here? Yes. Here. There you go. Thank you. Thank you, Reese. Can I mod? Yes, here you go. Yeah, you'll be a mod now every time. Belgian cops coming in here. You know, Grimace was pretty nice yesterday. I don't know what they're doing today. But basically, we saw them at first, we saw them as like these pulsar things. It's because they're, rotating, so you can't see their radiation all the time. You might see them at a periodic rate. And so we called them pulsars. So this is similar in the way in which we see pulses of light from a lighthouse whenever its rotating beams of light sweep across our location. So yeah. I feel special. Oh, special? At first I looked at that and I was like, flesh? Special. Okay, special. You are special. Of course, you and Doro, the most special. So there are, okay. So basically they're like lighthouses, right? Just like a lighthouse is doing its thing, but unless it's facing us, we won't really see it, right? It's like a lighthouse. So Similar to the way in which we see pulses of light from a lighthouse whenever it's rotating beams of light sweeping across our location, there are about 500 pulsars known to us. However, since the synchrotron beams of pulsars are fairly narrow, we expect the number of pulsars as seen from Earth to be significantly smaller than the number of neutron stars. Why are we sure that pulsars are rotating magnetized neutron stars? For one thing, we don't know of anything else that would produce such strong pulses of light at such short periods. So because neutron stars are also really compact, we expect that they're really fast at rotating and things like that, you know? So we think that the pulsars are basically magnetized neutron stars because what else? We don't really know of anything else that would produce such strong pulses of light at such short periods. If a pulsar were actually undergoing radial pulsations with a period of 10 to the minus 3 seconds, its density would have to be around 10 to the 16 kilograms per meter cubed. Denser than any known white dwarf. So people were like, okay, these are not white dwarfs. So it kind of went like, they basically went like that. Okay, let's keep going. There's a nice part coming in now. So it doesn't have to be, but I think, yeah, a lot of them are spinning. Yeah. Basically, if there was not any angular momentum to conserve, then it would not necessarily be spinning. But I think the way they, yeah, basically, I think this is the reason why basically, if there is a rotating magnetic field, which would then create an electric field, which then creates the synchrotron radiation, which then shows up as like a pulsar to like some certain requirements have to be met, but oftentimes they're pulsars. Yes, if that makes sense. A clinching piece of circumstantial evidence is that some pulsars are found within supernova remnants. Both, so I think it's not completely for sure known that you have to be a pulsar. But we've seen pulsars and we think that, oh my gosh, these have got to be neutron stars because of like other reasons. And so here's some more of that. A clinching piece of circumstantial evidence is that some pulsars are found within supernova remnants. Both neutron stars and supernova remnants are created as the consequence of core collapse in a massive star. So by the way, oh, thank you, Ben. Thank you so much. I do not comment much, but rest assured that I'm listening carefully. Thank you so much, Ben. Really appreciate you as well. Thank you. Ben, Reese, and Doro. And I'm sure I'm missing someone. Can their proximity to us be calculated in any way? Yeah. Yes. So basically, another thing I didn't really mention yet is because there are different types of supernova. The neutron stars are not really thought to be made unless you are doing a core collapse type of supernova of a very massive star, right? So it's almost like we've seen pulsars within supernova remnants, and we've also seen neutron stars to be supernova remnants. So let's briefly review events during core collapse. The vastness of your knowledge is actually insane. Rain Woman. Oh. Okay. So, well, I have all these books and authors who are sharing their knowledge, right? So, let's briefly review events during core collapse. So, by the way, so there are people who work on modeling supernovae, like supernova, right? And there are different ways of having a supernova. Core collapse supernova is a very common one. We just kind of mentioned it, right? And now we're going to briefly review the events during such a core collapse. The iron core of a massive star grows larger than the Chandrasekhar mass. So core collapse pretty much, so when somebody says core collapse, they basically mean a massive star who has made a core of iron. Like it's basically grown an iron core in its belly. And that iron core has become bigger than the Chandrasekhar mass limit, which is around 1.4 solar masses. So it's not just like oh, I'm gonna core collapse out of nowhere. Like it has an insanely Reese is just lying. He's like an electrical engineer and he has like a whole business. Oh, sorry. Did I say things about Belgium that I shouldn't? He does science for a living. Successfully. So he knows a lot. Ask him about batteries. I'm sure he knows about he knows everything about batteries, capacitors, inductors, circuits, electricity. The iron core of a massive star grows larger than the Chandrasekhar mass before a core collapse. No longer supported by degenerate electron pressure, the core starts to collapse. So basically, electron degeneracy pressure can't really support such a massive core anymore. Remember how white dwarfs are supported by electron degeneracy pressure. But the white dwarf mass limit is basically the Chandrasekhar limit, which is around 1.4 solar masses. If you're much bigger than that, if your core is much bigger than the size of a regular white dwarf, or around the Chandrasekhar mass limit, which is around 1.4 solar masses, electron degeneracy pressure can't really hold you together anymore. Protons and electrons now will combine to form neutrons, and 10 to the 57 neutrinos are produced in that process of where protons and electrons come together to make neutrons. All those neutrinos leave the star, carrying away energy from it. The collapsing neutron sphere is actually dense enough to be opaque to neutrinos, so it takes them a while to work their way out in a random walk. So if you're modeling this core collapse supernova, you'd have to model this as well. Basically, the neutrinos apparently have some trouble leaving this core, and so do a random walk out of the star. Next bullet, the neutron sphere is compressed slightly beyond the point where degenerate neutron pressure balances gravity and bounces back. So the neutron sphere is compressed slightly beyond the point where degenerate neutron pressure balances gravity and bounces back. Because at some point, you can't compress neutrons together anymore because a strong force is repulsive. So it's like gravity would have smooshed these things even more together, but the neutron degeneracy pressure, which is also ruled by strong force, doesn't let you come any closer than a certain point because the strong force is repulsive at smaller distances. The core bounce sends a shock wave through the outer layers of the star. So remember, we talked about shock waves when we talked about gamma ray bursts. So this is similar, okay? It's very interesting. When these types of things are happening at these scales and speeds, there's basically like shock waves now. The core bounce sends a shock wave through the outer layers of the star. After 30 milliseconds or so, the amount of matter swept up by the shock wave is sufficient to temporarily stall the shock's outward motion. Beautiful. After 30 milliseconds or so, the amount of matter swept up by the shock wave is sufficient to temporarily stall the shock's outward motion. The neutrinos making their way out of the neutron star interact with the dense gas in the shock wave, heating the gas and causing the shock wave to start moving outward again. Because it's almost like all this stuff sometimes balances itself out. It's like, like the core bounce sends a shock wave through the outer layers of the star. After 30 milliseconds or so, the amount of matter swept up by the shock wave is sufficient to temporarily stall the shock's outward motion. So the neutrinos are carrying away a lot of energy. They do interact through the weak force. They just interact weakly. They don't interact for the most part, but because this is a ton of neutrinos, they're basically taking all that energy out of the core and weaving it through the dense gas in the shock wave, heating the gas and causing the shock wave to start moving outward again. Basically, think of it as the neutrinos are carrying out some of the energy within that core. It's a ton of neutrinos. The energy carried out by this neutrino, so neutrinos interact through the weak force. It's a different kind of force, but they do interact, they just interact a lot less. But because this is a ton of neutrinos and they're carrying out an energy, which is an immense amount of energy, I think we said it was 10 to the 46 joules. That's how much energy the neutrinos carry out. That's more energy than the sun will put out during its main sequence, our sun. The outer layers are then ejected at high speed. So once the shock wave starts to move outward again, the outer layers are then ejected at high speed, up to 15,000 kilometers per second, or 0.05 c, where c is the speed of light. Electrician. So electricians know a lot about electronics. Nuclear fission, yeah. So nuclear fission is about breaking a nucleus. It's not nuclear fission quite that. There's a bunch of nuclear fusion that happens in stars, and then at some point, actually, we will cover nuclear physics at some point. You will see why the nuclear physics kind of stops. Helpful neutrinos, I thought they didn't interact with anything. Giving it a push. Splitting atoms? No. So basically, nuclear fission is where you actually split the nucleus of something. Right. like uranium is a very heavy nucleus. So if you go and split it, it'll be very repetitive, because every time you're splitting it, you make something that then goes and splits another thing. So breaking apart a nucleus, especially a very heavy nucleus like the one like uranium, like what they used in the atomic bomb, that's nuclear fission. Fission means to break the nucleus. Nuclear fusion is where nuclei are coming together to the chain reaction creates all the energy in nuclear fission. Yes, for something like the atomic bomb. Nuclear fusion is basically lighter nuclei coming together to make heavier nuclei. And remember, nuclear physics has some rules too. So there's certain things that we can discuss about nuclear physics that will make this star stuff make sense. Basically, certain nuclei are more stable, okay? So for example, we talked about binding energy at one point, remember about that? Basically, not all nuclei, so think about the periodic table, think about all the elements, and remember that the elements, you know, what a certain element is determined by how many protons there are in the nucleus. But at some point, you start to get more and more neutrons actually as well for the heavier elements. But basically, when it comes to the nucleus of something, remember how the same type of element can have isotopes, as in the different number of neutrons in the nucleus can give you an isotope of the same element, right? For example, for hydrogen and helium, deuterium, things like that. So then basically certain nuclei, so how stable a nucleus is depends on something called binding energy, and iron has like an amazing binding energy. So the iron nucleus is very stable. So the stars, pretty much the more massive stars, which has a lot of ability to gather together a lot of different smaller nuclei to make the heavier and heavier nuclei, the more stuff you have, the more you can make the heavier nuclei, right? Because you're literally combining multiple nuclei to make a heavier nucleus. And it requires some amount of energy to do that as well. So if you are a low mass star with not much, another part is about the heat actually. So if you're a low mass star, you're going to cool down and your insides are not going to be hot enough to do all the smooshing together of the nuclei. Okay, so there's like different factors. But basically nuclear physics is its own field, and certain nuclear physics is more allowed than others. Certain types of nuclear fusions are more better choice, more nature favored than others. And so getting this iron core, iron is super stable. That's why you basically end up with an iron core for something like a very massive star. It'll end up with a core of iron because iron is very stable as a nucleus. And then to make, remember, obviously there are elements heavier than iron, there are nuclei heavier than iron, and to make those elements, you generally need a different kind of process. There's whole different discussions of nuclear physics that we can do. Wow, Reese, you're a mod. Congrats. Yes, Reese is now a mod. So basically, this is now a nuclear physics conversation that we can go into more detail of, but hopefully that makes sense. I actually forget what you even asked at this point. What did you ask again? Oh, you asked about nuclear fission. Yeah, no, it's not nuclear fission. It's nuclear fusion that powers a star. And then once it reaches that level of an iron core, which remember is very stable, it's basically gonna stop doing as much nuclear physics or nuclear power as it needs to in order to support itself against gravity. Because if the nuclear physics or the nuclear fusion does not happen, then it will collapse on itself because of all this mass. It's vulnerable, it's susceptible to gravitational collapse. Okay? One interesting side effect of the shock wave. So we determined that core collapse has shock waves, a lot like the shock waves that we talked about in gamma ray bursts, remember? Because gamma ray bursts, depending on the type of gamma ray burst, is basically just a bigger supernova, right? The long gamma ray bursts are hypernovae or bigger supernovae, and the short gamma ray bursts are neutron star mergers, or neutron star and black hole mergers, or black hole mergers. Gravity wins if the star's fusion game is weak. Got it. Yes! Yes! Gravity wins if the star's fusion game is weak. Yes! Oh my gosh! You got it. Also, it's also a little bit to do, so you got the main point. That's the main point. The finer point is about the strong force, which is that you can't, the electron degeneracy pressure doesn't keep you stable after a certain point. So there's things like that as well, but that's less important at this point. So one interesting side effect of the shock wave is that it produces small amounts of elements. Ooh, are you ready for elements heavier than iron? So one interesting side effect of the shock wave is that it produces small amounts of elements heavier than iron in the shock wave. Small amounts, but nonetheless. It takes energy to create these ultramassive elements, but the supernova has energy to spare. If it's gonna die, might as well make something heavier, right? Another interesting side effect is that the expanding gas becomes hot and emits lots of light. So that's why a supernova is basically, it looks like a really bright star because it emits lots of light. The light emitted by the shock-heated gas is what we usually think of when we talk about a supernova. However, photons carry only a small amount of the energy associated with the core collapse. Here's a more complete accounting. So we think of supernova is I think supernova means like new star, or like this really bright star is how it got its name. But actually, the light we would see from a supernova is not even the main part of the energy that is released from a core collapse supernova. So listen to this bookkeeping. So the energy associated with the core collapse supernova is as follows. Neutrino energy, so the energy carried out by neutrinos. Oh, Suji mama, good girl. Good girl, Suji. Suji's drinking water, so I'm encouraging her. Good girl, my baby. So, neutrino energy. The energy carried out by neutrinos is 10 to the 46 joules. That's a lot. Kinetic energy of ejected gas, 10 to the 44 joules. Photon energy, 10 to the 42 joules. So photon energy is actually the least. This energy comes from the gravitational potential energy of the pre-collapse core. A neutron star has gravitational potential energy. of -3 times 10 to the 46 joules. This is about 10% of the rest energy of a neutron star, which is 3 times 10 to the 47 joules. Thus, compressing matter into a neutron star is a fairly efficient way of converting its mass into energy. At maximum luminosity, the supernova emits photons with a luminosity of around 10 to the 9 solar luminosities. However, the supernova decreases in luminosity by a factor of 100 over a few months. So if we see Betelgeuse supernova, Betelgeuse is a red giant. We expect it to supernova or die. At first, you would see a very bright star as in a bright spot, a bright star. I'm saying like this because it's a supernova. But then over the course of a few months, the luminosity should be kind of going down, you know. Supernovae are bright but brief-lived phenomena. We looked at gamma ray bursts, remember, even more extreme events in the sky, and they are super transient. Gamma ray bursts, the typical time period of a gamma ray burst is even shorter. It's of the order of like seconds, you know. Of course, there's some more details that we also discussed about that, but you know. An interesting tidbit of information is that the nearest star, oh, here we go. I forgot. They're about to talk about Betelgeuse. An interesting tidbit of information is that the nearest star with mass of greater than 7 solar masses. So Betelgeuse has a mass of over 7 solar masses. So it's a giant. And that's like a terminology in the life cycle of a star. What did you say creates gamma ray bursts? So gamma ray bursts, depending on the type of gamma ray burst, if it's a long gamma ray burst, it is basically from a hypernova, like a super big supernova. So the stuff we're talking about now, but like even more extreme. That's what makes a long GRB, long gamma ray burst. And then short gamma ray burst is from mergers of, so like super, it's basically from an explosion, but it depends like what causes the explosion, right? So the explosion in the case of a long gamma ray burst is either a hypernova, or in the case of a short gamma ray burst is basically a neutron star merger or a neutron star black hole merger. So like two neutron stars in a binary doing a dance together, revolving around each other, losing energy, will finally collide. And when it collides, there's massive amounts of energy released, an explosion, lots of drama. That's basically going to give you a short gamma ray burst. Or a neutron star black hole binary. Oftentimes, these things are in binaries. They're like a couple exploding together eventually. What a couple. So Betelgeuse, speaking of supernova, so Betelgeuse is a giant. It has a mass of greater than 7 solar masses, and it's at a distance of only 130 parsecs. When it becomes a supernova, any millennium now, pretty much Betelgeuse, when I was in undergrad, Betelgeuse was already due. Its flux as seen from Earth will be comparable to that of the full moon. When Betelgeuse supernovas and the light from it reaches us, we should be seeing a flux as big as the flux of comparable to the moon, to the full moon, because it's close. There haven't been any Betelgeuse scaled supernovae during recorded history. So during the history of us recording things, there hasn't been a Betelgeuse scaled supernova, but there have been some comparable in flux to Venus on AD 1054. So in the year 1054, July 5th, in the Julian calendar, a supernova appeared in the constellation of Taurus Chinese astronomical records report that the guest star had a flux corresponding to m equal to -4, around -4 in the system of Hipparchus. The supernova was also commemorated in an Anasazi wall painting. Today, nearly 1,000 years later, so this was in the thousands, this was in 1054, it is 2025 now, as far as I know. Nearly 1,000 years later, when we turn, nearly 1,000 years later, when we turn our telescopes to the position recorded by the Chinese astronomers, we see the Crab Nebula. If you've heard of the Crab Nebula, a supernova remnant. So that thing, that supernova in 1054, July 5, according to the Julius Caesar calendar, if we point our telescopes to that position where the supernova happened back then, we see the Crab Nebula, which is a supernova remnant. The Crab Nebula is 1.5 parsecs in radius, and its expansion speed, measured from Doppler shifts, is 1,500 kilometers per second. Wow. A little calculation soon shows that 1.5 parsecs is around 1,500 kilometers per second times 1,000 years. The Crab Nebula shows all the signs of being the expanding cloud of debris. It's an expanding cloud of debris from an explosion about 1,000 years earlier. So if you have an explosion, the nice thing is that the debris will slowly, disperse. And guess what? That's how we are here. If the debris from stars exploding did not go everywhere, slowly but surely, there would not be elements making us today. Yeah. Isn't that amazing? Yeah. I thought so. That's the usefulness of astronomy. It's not useful, but it's amazing. The Crab Nebula shows all the signs of being the expanding cloud of debris from an explosion about 1,000 years earlier. In the center of the Crab Nebula is a pulsar. Your favorite. The Crab pulsar has a period of 33 milliseconds and is seen to pulsate at radio, visible, X-ray, and gamma ray wavelengths. The pulsar is in the Crab Nebula, just where you'd expect the neutron star. It's a classic smoking gun piece of evidence that neutron stars are basically pulsars and pulsars are neutron stars. So the Crab Nebula, so why is it a Crab Nebula? Because there was a supernova there. The debris over time, over 1,000 years, has been expanding and dispersing. So it's no longer just a compact thing. It's been kind of like going everywhere. So we see it as a nebula. We call it the Crab Nebula. It's famous. And so it's this more extended thing that we're picking up on. And in the center of the Crab Nebula is the evidence of the death of that star. That star eventually died down to a neutron star. It's a pulsar. Because stars, when they die, they eventually become a remnant. It's either a white dwarf or a neutron star or a black hole, depending on the initial mass of the star. This was a pretty massive star that exploded, that died, leaving behind a neutron star. The Crab pulsar has a period of 33 milliseconds, so it's not too bad, 33 milliseconds, and is seen to pulsate at radio, visible, X-ray, and gamma ray wavelengths. Wow. So you can pick it up with all of that. You know what I mean? Like the detection can be in any of it. And I'm sure they, built it. The pulsar is in the Crab Nebula, just where you'd expect the neutron star. Curiously, astronomers had been observing the pulsar for years at visible wavelengths without noticing the strobe effect. The pulses were too fast. So if you looked at the pulsar at other at the visible wavelength, you might not see all of the effects of it. They had to eventually see it in radio, visible, X-ray, gamma ray. That's why we say multi-messenger astronomy. Like, you want to be using multiple parts of the spectrum, whether it be light and maybe even completely other particles. That might also give you some indication. Wow. Thanks for carbon dying stars. Yeah, I mean, not just carbon. Stars that make carbon, that make iron, that make more than iron. All of that stuff can die and make us. Did die and make us. I remember reading something about that golden disk we sent on that craft in the hope of aliens finding it. Voyager and how it described our position using neighboring pulsars. Oh, I don't know about that, but yeah, maybe. Maybe. So that's neutron stars. Hi. Welcome to the live. Thank you for joining. Thank you for 20 likes. How nice. Thank you for staying on the live and listening about, I was going to talk about particle astrophysics, but you, Reese, asked about neutron stars, and so I launched into this discussion. I think that's all good because this was an incredible, interesting discussion. I loved it. Hopefully you liked it too. It had recordings of human voices and famous music, etc. Oh, okay. Yeah, I don't know. That sounds interesting though. I always enjoy your lives. They're fascinating. Thank you. And now you're a mod. I should have done this sooner. Thank you for offering to be a mod. I kind of forgot about mods. I mean, that one time I had a really strict mod, but usually they're kids and they don't stay up this late. So for this particular live with the physics, usually I think in the past we didn't have much issues with people kind of being too disruptive, but I think, yeah, no, this is a good development. You're a mod now. Yay, thank you so much for modding. So, yeah. I won't be as trigger happy as that other mod. Oh yeah, he's a kid. What's his name again? Death Dragon. Death Dragon is like, he's like 8. He loves, yeah, he loves banning people. One time, I know, bless him. One time, he like banned almost everyone. So, yeah, he even bans like my like other like little girls on the live, and I'm like, oh my gosh, let the girls learn physics. There aren't many of them. So, unfortunately, I think I had to take him off at one point. But then also, this is way past his bedtime, so makes sense. Yeah. So anyway, thank you so much, Reese. As usual, whenever you join, the nice and good questions always lead to more discussion, which is really helpful. I think pretty much in the month of November, when I was covering the Einstein's Cosmos book by Michio Kaku, and we looked at all the 20th century developments, I think a lot of the questions you had asked at that point had also led to more discussions. So if people are catching this later on and you want to hear the modern physics discussions, that we did way back in November, October maybe-ish, then feel free to go back and look in the live tab for that. Thank you as usual for joining us, and staying with us in the live and watching this as a video later on. Thank you so much. And yes, because you asked about neutron, I think it was neutron stars that you asked about. And also, I'm glad we covered neutron stars today because neutron stars are not really stars. They're stellar remnants. So it's good that we talked about death of stars and how stars die, and sort of a little bit about the life cycle of stars and core collapse supernova, which is a very common way of a star to die, and mainly the very important relationship between mass and everything to do with stars. Pretty much has to do with their mass, and like various radii and things like that too, the size of stars. And also pretty much the yes, and also pretty much the different types of stellar remnants that we covered. I think we'll talk about black holes tomorrow, but basically, yeah, stellar remnants are white dwarfs, either white dwarfs or neutron stars or black holes. If I ever go quiet in the lives, it's because I've fallen asleep. Sometimes I'm exhausted, but I always try to catch the streams when I can. Thank you, Reese. I know. We're old buddies now, so I know that you are falling asleep in Belgium when you are quiet. That's all right. You should fall asleep.